Okay, so good morning, everybody. Good evening, everybody. I just received an email from Sabir Ali. He said, I'm not getting the connection. What does that mean? I don't know. Any of you have, did you have trouble?
He told he is not able to connect to Zoom. Zoom is through Zoom, yes.
I think he has to sign up for Zoom. Like you have to authenticate.
Oh,
Yeah. I've done that because otherwise, I mean, maybe that's why I'm getting so few people.
Yeah, that's
okay. Okay. So yeah. So last time we talked about. I explained to you what this holonomy is, where it comes from, and then gave you this physical picture of what a non-trivial holonomy encodes. And then I talked about the effect of gauge transformations on a non-abelian connection. So I hope that you all found the time to sit down and derive this. And then we have this gauge connections on manifolds with boundaries. So again, I will come to that at some point if I have the time. Then we have this omega spin connection, which is a SL2C connection. And we saw that we can solve for this spin connection entirely in terms of the tetrad. And then we can define a generalized covariant derivative, which acts both on spatial indices and on these internal indices. And we can find the curvature of this tetrad when it acts on something with spatial indices. And if we do that, we find out that, well, that just gives us the Riemann curvature tensor. On the other hand, we can look at the curvature of this connection when it acts on these internal indices. In that case, we get a curvature which has two internal indices. And these two curvatures, right? So then we can look at this expression again, and well, this is given by this. Now we take this V and we can write it as something with a purely internal index contracted with a tetrad, right? So tetrad is a soldering form, so it allows us to map between the tangent space and the internal, the fiber. And then we use the property that the tetrad is parallel transported by the connection or annihilated by the connection to bring it outside these derivatives. And then we can use the fact that this expression is given by this curvature acting on the object with an internal index and raising and lowering one index with another copy of the tetrad. We find that one can relate the Riemann curvature tensor to this gauge connection curvature tensor. And the connection is, and the relationship is very simple and very obvious after the fact that these two are simply related to each other by their soldering form, right? So they encode exactly the same information. And so therefore you can also find out, write down the Ricci curvature and so on, Ricci scalar in terms of this gauge curvature. And finally, we can write down the Einstein-Hilbert action in this manner. Okay. Now, I gave you some references. One was this Ashtekar-Lewandowski paper. Then, of course, Thiemann, Intro to Modern Canonical Quantum Gravity. And then my little book with Sundance. There is also a very nice paper by Romano, I think Romano was the one of the students of Ashtekar, but what happened to him, I don't know. So anyway, he has a very nice paper. It's called Connection Dynamics versus Geometrodynamics, and it's an old paper at this point in time. It's from 90 something like 90 what is it 93 1993, right? So it's 27 years old, but it's a really good reference. It's on archive. He works out all of these details very nicely. So okay, now so then this expression, now it is written in terms of a gauge connection and the tetrad, but it still has this expression for the metric here. So we can get rid of that expression for the metric by using these antisymmetric volume forms, right? So I'll talk about that in a second. Then we can ask how to find the equations of motion. So the equation of motion, you just do the variation with respect to the connection, and the tetrad. If you do the variation with respect to the connection, this just gives you the metric compatibility condition. It just tells you that the tetrad is annihilated by the gauge covariant derivative. And if you do the variation with respect to the metric, you get, well, this equation, and you substitute this equation in here, and you do some algebraic manipulations, and you end up with the final conclusion, which is that G mu is equal to 0. Okay. And to do this calculation, it is helpful to use this identity, which relates the change in the curvature due to a change in the connection. So this is, I read somewhere that this is called the Palatini identity. So I'll call it that. This is the Palatini identity. Okay. Okay. So now let's see. Now what we want to do is we want to write down our constraints. So we want to do our 3+1 formalism, and right. And before doing that, we can make a note of one more point. So let me, lecture 7. Which is that how do you relate this determinant of the metric to the tetrad? And the answer is quite straightforward actually. So you can write, you have this expression that if you take the tetrad, right, and you contract it using this Minkowski metric, you get the space-time metric. Okay. So here eta ij is equal to diagonal 1, 1, 1. All right. So now if you ask what is the determinant of G, right? So it's going to be the determinant of eta times the determinant of E, and then this whole square, right? Because it's the product of these matrices. So the determinant will be the product of the determinants, right? So the determinant of eta is minus, and this gives me det E squared, right? So we have that det E, determinant of E, is equal to root of minus G. So if I want to put this in the Einstein-Hilbert action, now I can write this as kappa d4 x. So root minus G becomes det E, and then I have f nu j right? And so now this is expressed purely in terms of the tetrad and the connection. Okay. So are there any questions at this point?
Is this part any action valid for any dimensions or only for...
No, so this is for 4 dimensions. So if you look, so this is for 3 plus 1. So if you look at 2 plus 1, for instance, okay, there it takes it looks like this, I believe, det E, and then you have 1 copy of the tetrad. So E mu I. So let me actually look at, Romano has a nice, right, looks like this. Mu gamma in jk and then epsilon I jk. So in 2 plus 1, it looks like this. Okay, so there is only 1 copy of the tetrad.
Why is there a difference?
The difference is because, okay, so let me write the constitutive equation again, okay, which is that R mu nu ij is equal to R A B C D, okay, sorry, R mu nu gamma delta E gamma I E delta j, okay. So where you understand that this is the triad now, or the tetrad, and this is the inverse of that, okay. Now if you want to define the volume element, okay, how do we do that? Well, we can take the completely antisymmetric tensor epsilon ijk. Okay, so this is plus 1, minus 1, or 0 if is even, permutation of ijk is odd, and otherwise, right? And in terms of this, we can, using this completely antisymmetric tensor, we can define the following quantity using the this. So let's say that we are working in 2 plus 1 now, okay, in 2 plus 1 dimension. So this is the triad, 2 plus 1 triad, okay. Epsilon I, epsilon mu, mu, or let's say eta, okay, this is equal to epsilon mu nu eta. All right. Now this this expression gives us this completely antisymmetric tensor, right? And this actually measures the volume of your space-time, right? Because if you recall that if you want to do if you want to perform a volume integral, right? What do we actually do? We take a so let's say whatever dn or d to the power d plus 1 x, and then we take mu n and or to the power d plus 1, and we have some n form or d plus 1 form. All right, so let me again. Right. So, and this quantity, this completely antisymmetric tensor, it can be written as mu1, mu2 to mu to the d plus 1 times root of the determinant of the metric, whatever that metric is, times dx 1 wedge dx2 wedge dx d plus 1, like this. Okay. So if I do this, if I take this expression, right, what this gives me is precisely this volume form. Okay. So if I want to write down the Einstein-Hilbert action, now what I would do is, in the Einstein-Hilbert action, this is the integrand, root of minus g. Okay. And now what is this root of minus g? I would write it as, let's say, root of minus g r a b c d. And now I have to contract some indices. I have to contract a and c, and I have to contract b and d. So I would write delta bd and delta ac, and these are antisymmetrized. Okay. And now this expression, okay, so this is a bunch of formal, these are a bunch of formal manipulations. This expression can be written using the following identity: epsilon dce and then eta bae, where this eta abc bae is the inverse of this tensor. And now this expression, again, I can write it using this. So if I insert this expression over here, sorry, so yeah, root, this will go away. Then I will get r a b c d epsilon I j k, and I'm making a mistake with my indices. But your question, to answer your question, why is there one copy of the tetrad? It has to do with the fact that, well, I'm not sure how to state it. I suppose it has to do with the fact that when you write down this determinant of the metric, right, it is related to the determinant of this tetrad, right? So how do we write down the determinant of any matrix? Let's say I have a matrix AB. Okay, how do I write down the determinant of AB? We have a general expression for this. It can be written like this: B1 to Bn, and then A, B1, A2, B2, so on, A, B, A, and Bn, right? This is the expression for the determinant of any matrix. And then there is I can again multiply by A1, sorry, I write another copy of this, right? So if you ask what is the determinant of the tetrad, right, and or the Vierbein. So if you are in 3 dimensions, right, the determinant will take the form epsilon mu nu delta e mu I, e mu j, e delta k, and then epsilon I j k, right? And if you are in 4 dimensions, you will get 4 copies of the tetrad in this expression. So you will get epsilon mu nu delta gamma, mu I, mu j, delta k, gamma L, then epsilon I j, KL. Okay, I might be missing some 1 by 3 factorial and 1 by 4 factorial, right? So now 2 of these copies, they go into contracting the indices on the curvature tensor, right? Because if you have the curvature tensor, you want to write down mu nu ij. To convert these 2 indices, what do you use? You contract with 2 copies of the tetrad. So you do something like mu nu gamma I E delta j, right? And then there is 1 copy of the tetrad that's left over. So if you are in 4 dimensions, 2 of these copies of the tetrad go into this contraction, and then you will have two left over. Roughly speaking, this is the reason. So if you are in 5 dimensions, your Palatini action will look like this, d5x. You'll get E wedge F. You'll get 3 copies of the tetrad contracted with and then you have to take the trace of all of this. Okay.
So you mean as long as we write the as long as we use determinant E in the expression of Palatini action, then it's
right.
general in any dimensions?
Sorry?
So if we want to write the determinant of E as a product, wedge product of tetrads, then the expression should depend on the dimensions. But
yeah, of course, because of the fact, yeah, because of the fact that if you take the determinant of any matrix, if you take the determinant of any matrix, it has this form, right? It contains n terms,
right?
Where n is the rank or is a dimension of the matrix, right?
So if we kept the determinant E, just if one kept determinant E in the action, then the expression is just general for valid for any dimensions.
I don't know. Honestly, off the top of my head, I don't know. I'll have to look into that.
Okay.
Okay. So your question is that if I just left it as det E, what would I get? I mean,
yeah,
okay. Okay. So now coming back, where were we? We were talking about right. So now we want to do the 3+1 decomposition, right? So we have the Palatini action, which is, where is it? This is the Palatini action. And now we want to perform the 3+1 decomposition, okay? So now to perform this decomposition, again, the procedure is that one would introduce to find the Hamiltonian, you introduce in exactly the same way, you introduce a lapse, right, a shift, and so on, right? You perform the foliation in exactly the same way. Normal unit vector and time evolution vector field. Okay. So now what one would do is you have to make a splitting of the tetrad, and for the splitting Okay, so in order to perform the splitting, we can write down, let's see. Well, I won't go into the details of the splitting, okay, because that becomes a little bit involved. So you can find the details in, for example, Romano, or you can find them in Thiemann, or you can find them in Ashtekar Lewandowski. Okay. So the question is, what happens when we finish the splitting, right? We'll end up with something where the the 3 metric and the extrinsic curvature, these are our the variables which will coordinatize our phase space, right? So now the question is, how are these variables related to the tetrad? So now I have this tetrad. What happens is that I choose this, when you do this, perform this splitting, it breaks up into a triad. So this is a triad. A is a spatial index, and this I is a SU2 index. Okay. So, roughly speaking, what is E mu I? E mu I consists of, you have this, if you write it as a matrix, right, you will get 0, 0, 0, 1, 0, 3, E1, 0, E3, 3, right? So roughly speaking, when you perform the splitting, if you look at the spatial part of this tetrad, what you're doing is you're looking only at this portion, right? The space-like portion. And here the components are like this. So E, 1, 2, 2, 3, 1, 2, 2, like this. So this is the triad. All right. This is just the same way that when we look at the metric, for instance, if you look at the metric, the full 4-dimensional metric, right? You have this portion, which is H, right? And this becomes a 3 metric. At least as long as you are in a set of coordinates in which the time-like components of this H, this tensor vanish. So the same way, you can define the triad as this portion of the tetrad. And now you have this extrinsic curvature. So what is the relation of the 3 metric to this tetrad? The 3 metric can be related to the tetrad in exactly the same way that you relate the 4 metric to the full So if you have G mu nu, you write E mu I, E mu j, eta ij. Here, now what you have done is you have gone from 3 plus 1, the full 4 dimensions, to the spatial part only. So if you look at the spatial part, your Minkowski metric will just reduce to the Kronecker delta, right? And you'll be left with spatial indices. So the relation becomes exactly the same, right? Now your tangent space is not Minkowski space anymore. It is just R3. And instead of SL2C, you have reduced down to SU2. Okay. And from R31, you have reduced to R3. Now we have the other degree of freedom, which is the extrinsic curvature. So we want to introduce something expressed in terms of the tetrad. So what we do is we introduce a extrinsic curvature Lie algebra valued form. So this is a Lie algebra index, and this is the the spatial index. So this becomes a Lie algebra valued one form, and we contract it with the triad like this, Bi, right? So, or if you wish, you can raise this index and contract it in this way. So this is a Lie algebra valued one form. Okay. Now we have the condition that KAB is symmetric. The extrinsic curvature is a symmetric tensor, right? This is a very important condition. This arises because of the fact that when you have a hypersurface orthogonal vector field, which is a unit vector field, unit normal vector field, and you define this extrinsic curvature, if you remember, as the spatial projection of the covariant derivative of this unit normal vector field, right? So when you do this, then Frobenius's theorem, so there is something called Frobenius's theorem. It tells you that KAB, the antisymmetric part of KAB, is 0. Okay. This Frobenius theorem actually I've covered in a set of notes that I posted on Zulip on the Gauss-Kodazzi constraint and other topics like that. Okay. So we have this constraint on KAB that it has to be symmetric quantity. This constraint can be expressed in the following way in terms of this Lie algebra valued one form. So we can write KAB, we can invert this equation. This equation we can invert it to write it in this way. KAB J, like this, delta I. Right? So this is the inversion of this equation, right? And now the fact that KAB is symmetric means that if I take the antisymmetric part of this equation, which is EI KB J delta IJ, this has to be equal to 0. So this is a constraint on this extrinsic curvature one form. And I will write this constraint as GAB is equal to 0. The reason we call it G is because G for Gauss. This will take the form of the Gauss constraint, and we will see how that happens in a little bit. Okay. Now the next thing is that we have this triad. Using this triad, we can we define another field which looks like this: 1/2 epsilon ABC epsilon ijk EA, sorry, EBJ ECK. Now, what is this quantity? This is basically you're taking the cross product of these vectors, right? These are two vectors, and you're taking the cross product. And this quantity is actually a bivector, and you're taking the dual of that bivector to write down a vector, right? And this bivector represents the area to form. Okay, the reason for this is that you imagine that you have a triad. Now a triad looks like this. You have three vectors E1, E2, and E3, right? They form a basis of your three-dimensional space. Okay. Then if you take E1 cross E2, what does that give you? That gives you the area of this parallelogram, right, which is spanned by E1 and E2. And this quantity is like the normal to this area vector. So we are going sort of into something which is the dual of the tetrad or the triad, right? So instead of working with a triad, it becomes more convenient to work with the bivectors which are formed from the triad. And the bivectors are basically the area normals to surfaces, right? So in 3 dimensions, this is something that you can do in 3 dimensions, right? The fact that U cross V is equal to W, this identity is only true in 3 dimensions, right? So what is U cross V? We write it as epsilon ijk ujvk, right? This is the cross product. But let's say you are in 4 dimensions. In 4 dimensions, you will get epsilon ijkl ukvl. This will be a 2 form now, because there are 2 indices on the epsilon which are left uncontracted. So it is only in 3 dimensions that you have this duality between vectors and bivectors, right? So that is what we will use. Okay. So using this quantity that we have defined, this epsilon, we can express this constraint as follows. So we have this constraint. I can express it alternatively in the following manner. I can write this as epsilon ABC EAI KBJ delta IJ, and then this becomes BC. This is equal to 0. Okay, and then I can use where is it? Right. So then I use this definition of E multiplied by 1 copy of the inverse tetrad, and finally I get my constraint can be written in this form: Ka I E A J is equal to 0, which is also the same as writing Gk is equal to epsilon, again using this bivector duality, into Gij is equal to 0. So which is equal to Ka epsilon Kij KAI ENJ equals 0. Okay. So we can express, we have expressed the intrinsic metric in terms of the triad. We have written the extrinsic curvature in terms of the triad. Right now, but now we have to translate all of that into this capital E, right? So if you write down the metric in terms of this capital E, what you get is the following. It becomes the det E times EA I EBJ delta IJ. So it's the same expression as before. Only thing is now you get a factor of delta E of determinant of E. Now what about the momentum pi AB? So pi AB is KAB minus K times HAB. Okay. This becomes, using the same delta det E EK EDK KJG delta BC CJ. Okay, so you take this expression for KAB and HAB, and you find that, well, your momentum variable can be written in this way. All right. And now we can write down the expression for the Hamiltonian constraint and the diffeomorphism constraint. So the diffeomorphism constraint which was HA is equal to the covariant derivative of this. So HA is equal to DB phi AB is equal to 0. And pi AB is equal to 0. This is the diffeomorphism constraint, where this is the three-dimensional covariant derivative. Not the one with the connection, but the one defined using the Christoffel symbol. Now, if you write this constraint using our these variables, what do we get? We get the constraint can be written in this following form. Again, we have this covariant derivative, then Kj E delta J minus delta AB. Now, all of this is very, very dry and very formal and very boring. Okay, but one has to go through this procedure. In the same way, you have the Hamiltonian constraint, right? And the Hamiltonian constraint, just to remind ourselves exactly what the Hamiltonian constraint was, it had this form, minus root h, the Ricci scalar, the three-dimensional Ricci scalar plus 1 by root h, and then some products of the momenta in this form, pi square. Now, again, if I translate this into the coordinates that we are using right now, which is in terms of this this densitized triad. So this E is called a densitized triad. Densitized triad. Yeah, Mustafa.
Yes, could you go over the first time you introduced the densitized triad? I just wanted to look at that definition once again. Yep. So here, I understand the expression that you wrote below, that you can write down the cross product as this epsilon and the two vectors, but I do not understand the second epsilon that's there. Could you explain that, please?
So let's see. So you have, okay. So you have these vectors, right? So I guess it is the let me write it out properly. So we start with this triad. Okay, let's take two of these vectors. So A and B are the label the vectors. Sorry, I and J label the vectors. A and B are the components, the space-time components. Right. So if I want to take the cross product of these two vectors, what would I do? I would say epsilon ABC. Epsilon IJK EAI EBJ. Right. This would give me something which has one index, one upper end, one this thing, internal index, right? But now the thing is that I have three tetrads, right? And if I do this with all, I have to do this with all three tetrads, right? Basically, because so you are left with an object which has one upper index and two lower indices, right? So then what you are doing is you are just taking the dual of this ABC UABK, and that gives you this CK.
Okay, I had one more question, and,
Okay.
and
So,
that is yep.
Let me just, so imagine that you have a tetrahedron, okay? And let me label these edges by E1, E2, and E3, right? Then E1 cross E2 will give me a vector which is, let's say, pointing like this. Okay. So if instead of writing it as E1 cross E2, right, it will be some vector as U12. Instead of writing it as U12, I can also write it as U3, where I get the 3 by just taking the, I'm putting one more factor of epsilon, right? So otherwise, each face would be labeled, each one of the bivectors would have two indices. Okay.
Yep. Thank you.
Okay. So you can just Devamalya is you're not seeing the screen. Let me start the screen.
For others to stop their video sharing, that's is it possible for others to stop their video sharing?
For whom? Others being whom?
Who are actually make their video on so that the bandwidth.
Why? No, it doesn't. Bandwidth is not really affected. Seriously, bandwidth is not affected. It's a very small amount. But I will ask everybody to turn their video off. Even I can turn my video off. It doesn't affect. If you cannot see the screen, then most likely you have to you probably just have to reconnect. Did you try reconnecting, Dev Malya? I think he's trying to reconnect. Let's see, 1 second. And Mustafa, what was your question? What was the second question?
Yeah, my second question was also related to the definition of the densitized triad. Could you go to that again, please?
Sure. Yeah.
Yeah. So my question is it fair to view the densitized triad as sort of a one form if I say that the triad is a vector?
1 second. Deva Malya, can you see the screen now?
Yes, yes. Now it is okay.
It's okay, right? Okay, good. If I scroll up and down, is it visible? You just tell me, okay?
Yes, yes. But
Okay.
I have a question after Mustafa, I think,
Sure.
asking the question,
Sure.
then I will ask.
Sure. Yeah. So Mustafa, your question is it fair to think of this as a one form, right?
Yep. If I consider the triad to be a vector.
Right. I mean, it is a one form, right? Because you take the cross product, you get a two form. You're taking the dual of that two form, you get a one form.
Oh, okay. Thank you.
Right. Deva Malya? And yeah,
Yes.
people can turn their videos on. I don't think it will affect the quality of the streaming. Yeah, Deva Malya, what's your question?
One thing, just I missed the arguments because of this disturbance. The density after that densitized one form or two form. What you have talked about. Just I have that. Okay.
Right. So okay, I'll go over that again. Okay. So we define this quantity.
And one more thing, that what is the meaning of diffeomorphism constant?
Right. So the diffeomorphism constraint, I had explained earlier. It generates if you take the Poisson bracket of the diffeomorphism constraint with any field that is defined on the hypersurface, spatial hypersurface, it generates the Lie derivative of that field with respect to the shift vector field. So
okay. So this is
let
called the
diffeomorphism
transformation.
1 second, let me write that down. So if you take the smeared diffeomorphism constraint, so the smeared diffeomorphism constraint looks like this: D3x NaHA, where HA is equal to this covariant derivative by A B like that. Okay. So if you take this with any field that is defined on your spatial hypersurface, then this generates a Lie derivative of your field, right? And that is exactly a diffeomorphism.
Okay.
It is a diffeomorphism generated by the.
So the diffeomorphism is expressed by the Lie derivative of the function.
You're right. Right. And this property is actually very very general.
Yeah.
If you can think about this in quantum terms or classical terms also. In quantum terms, if you remember, for instance, if you look at the Schrodinger equation in the Heisenberg representation, right? For any operator, you have this equation, right? Something like this. Right?
Yes.
So how do you interpret this equation? This equation tells you that the commutator of these two quantities, right, gives you the derivative of this quantity with respect to the vector field which is generated by this H. Okay, so the same way I have this function H. What is the vector field that is generated by this function? This vector field is NA.
Okay.
right? So this is true in general, that if you, and very often when you read about symmetries and so on, you'll see something like this. You'll see that there is some h, some operator h, and something like this, and you will see an expression of this sort, right? And again, this is the same statement. It is telling you that if you take the commutator, what you're doing is you're measuring the change in this operator due to this effect of this edge. Okay. One could of course reverse the argument also. But, okay. So I hope that I mean, as to why the Lie derivative corresponds to a diffeomorphism, again, why Lie derivatives give you diffeomorphisms? Well, this is the, I can suggest that you read up in Wald in the appendix on Lie derivatives, and then another very good reference is Schutz, Mathematical Methods for Physicists. So this is the book which I referred to when I was first learning about this, and from where I actually understood the concept of a Lie derivative. So Wald is not that transparent if you're trying to understand these concepts for the first time. But Schutz, this is the same Schutz. This is Bernard Schutz. This is the same Schutz who has written the textbook First Course on General Relativity, which most people use as an introductory textbook on general relativity.
I have his book on differential geometry, actually, not the general theory of relativity.
Right. So I think it's this book only, Mathematical Methods for Physicists.
Okay. I will see that.
I think so. Yeah, it's a thin little book. Okay.
So may I disturb?
Yeah, of course. This whole exercise is for people to ask questions and to learn only. Yeah.
Thing is, I have read the definition of the diffeomorphism is this is a bijective mapping of one manifold to another manifold. That is, the inverse mapping is also the differentiable, and that is onto, but that is bijective actually. So, but I understand that is a Euclidean translation is kind of a diffeomorphism, but so rotation is a diffeomorphism transformation, or is it not? Because
rotation is also a diffeomorphism, right?
Okay.
And see, so in particular, if you think about rotations and translations, then what you have is this notion of killing vector fields.
Yes. Yeah.
So killing vector fields, right? They satisfy this. What the property of a killing vector field is that if you have this vector field zeta or whatever this character is, right? Its action on the metric gives you 0, right? So the metric is so this tells you that this is a symmetry of your manifold. Well, the symmetry of your space-time, because it is your manifold plus the metric. So when you look at rotations, for instance, when you look at flat space, you have 6 different killing fields, killing vector fields. You have 3 rotations and 3 translations. And they all generate diffeomorphisms, right?
Okay.
I mean, in the case of rotations, there might be some issue with the diffeomorphism at the origin, but I mean, again, that can probably be resolved by excising the origin or something like that from the manifold. Is this okay? Please ask because because these questions are important. We are doing
Okay.
we are studying quantum geometry. We are studying the theory of quantum geometry. So the geometry part is the most important part.
Yes. Thank you. Deepak.
And yeah, I don't know if this clarifies it for you or not.
No, it's okay. It's okay. I've just the concept on the car space time. That's why I've read some.
Right. So in curved space time also you have these symmetries. So for instance, if you have a Schwarzschild black hole, in the case of a Schwarzschild space time, you have the 3 rotation vector fields. Those are the Killing vector fields, right? And the translations do not generate any symmetries, right? It's not translation invariant. And then if you have a Kerr black hole, then you have 1 Killing vector field, which is the rotation around the axis. Right? Right. Because the rotational symmetry is broken, so you only have one. So all of these, they generate diffeomorphism, right? But any vector field generates a diffeomorphism, not just a Killing vector field, right? This is the important thing. Killing vector fields generate isometries.
Yes.
Killing vector fields generate isometries, which preserve the metric. But a diffeomorphism doesn't have to preserve the metric, right? Diffeomorphism is just a continuous map of the manifold from one manifold to another manifold. That's it. It's just a differentiable mapping. That's all. So that mapping can do lots of things to the metric.
Yes.
Right. So any vector field on a manifold generates a diffeomorphism.
Yes.
More precisely, one should call it an automorphism, I think, because it's from the same manifold to itself. Okay.
Okay. Thank you, Deepak.
Okay. So now we have our.
Oh, can I just one question?
Yeah. Please.
When you talk about densitized triad,
yes.
If you want to generalize the higher dimensions, then is it become codimension 2 form?
Right. So that's related to the point that that Mustafa had raised. That why are we multiplying by this? If it's just the cross product, why are we? What is the second factor of epsilon doing in this picture, right? If you're just taking the cross product, you don't need 2 epsilons, right? If you just take the cross product of 2 vectors like u and v, you get 1 copy of epsilon, right? So you put in that second copy of epsilon so because the cross product gives you a 2 form, right? So to take that 2 form, you map it to a 1 form. That's what the second epsilon does. Right? So here your J and K, these indices, they label the vectors. B and C, they label the space-time components of those vectors. Right? So when I take the cross product, what do? I do this, perform this. Use this epsilon to contract these 2 indices, the components, right? But then I'm left with with this 2 form, and this is a 2 form which is living in that internal fiber. This is a 2 form which is living in that that Minkowski space, which is spanned by the triad, or not the Minkowski space, the R3, which is spanned by the triad. Right. So this is not a space-time 2 form. This is you can call it an internal 2 form. Okay. So if you are in in higher dimensions, then again, yeah, then in that case, you would have another index in this epsilon, and you would have another index in this epsilon also.
Okay.
Right. So there it wouldn't really make that much of a difference to write it whether you write it as a one form or a two form. So in fact, we will see later on when we talk about the Palatini action, there is something called the Holz modification. So we will look at the wedge product of tetrads. And on the wedge product of tetrads, we will define this duality operator, the Hodge duality operator. And using that, we will rewrite it again. And like you said, we will introduce this something which is analogous to this densitized triad, but it will be a two form. And well, you have to keep it as a two form.
Okay.
Okay.
And I have another question.
Yeah.
You talk about the spin connection or tetrad, then you say SU2 or SL2C rather than SO1,3 or SO3.
Rather than what? Sorry.
I mean, when you talk about internal degrees of freedom, you say SL2C rather than SO3,1.
Oh, right.
Why that? Is there any difference?
Well, SL2C is the double cover of SO31.
Yeah.
Just like SU2 is the double cover of SO3.
Right. And why do we need to think on double cover rather than?
Because you can, with SL2C, you can work with spinners. Right.
Okay. Yeah, that's right. And so, well.
So SO31 is, if you work with SO31, you have to work with vectors, right? 4 vectors.
Yeah.
But with SL2C, you can work with spinners.
Yeah, that's right. Right. I understand. Yeah.
Right.
Is it always does always well does the double cover always exist in any dimensions?
I don't know the answer to that question, so I'm not going to try to answer it.
Okay. Thank you.
Okay. All right. So one important point is that I have completely skipped the whole 3+1 decomposition process in this tetrad language, okay, the Palatini language. So this might appear as a unjustifiable shortcut, but then if I did that, it would not necessarily give us any more insight. Instead, what I have done is I've gone straight to rewriting the phase space variables which we get from the 3+1 ADM decomposition in terms of our connection and triad. Okay. So now we have written the 3 metric. We can write the 3 metric in terms of this triad. We can write the extrinsic curvature in terms of this triad. Okay. So here to write we just take the triad and we contract one index with the soldering form. We get this extrinsic curvature, which is a Lie algebra valued one form. Right? It's a one form because it has one space-time index. It is Lie algebra valued because it has one Lie algebra. Then, if we invert this to write down this curvature tensor, then this curvature tensor being symmetric, its antisymmetric part must vanish. This requirement becomes a constraint, and this is a new constraint. This constraint was not present in the ADM formalism, in the using metrics. This constraint because there it is automatically satisfied by the curvature, extrinsic curvature tensor. In this case, it is not necessarily true. You have to impose it as this constraint, and this constraint will become what we call the Gauss constraint later. So in terms of the densitized triad, the Gauss constraint can be written in this form again, and the diffeomorphism constraint again takes some form which involves products of the extrinsic curvature one form and the densitized triad, and the Hamiltonian which has this form in the ADM variables. So the Hamiltonian becomes, again let me write it down, the Hamiltonian looks like this, minus det E square times 3R, okay, plus 2 by again det E squared, and then something like this, KAG KBL, then EJ EL AB antisymmetry. Okay, so if you compare it with the expression that you have from the ADM case, so paste, delete. Okay, so this is the connection variables, and this is the metric variables. Okay. Right. So it looks, so actually, yeah, there's one factor of det E, not two factors, I think. So you have, it looks the same. I mean, you have the Ricci scalar, the three-dimensional Ricci scalar, right? And then you have this term involving the momentum when written in terms of these one forms, it takes this expression. Okay. So again, now at this point, these expressions, they don't necessarily look all that transparent. This is in the connection variables, and then the metric variables. It will look like A is equal to pan. So, but we have not yet, these are not the Ashtekar variables, okay? We are not there yet. So what we have done is we have defined a new set of coordinates on our phase space. What are these coordinates? They are this densitized triad or co-triad and this one form. These are the new phase space coordinates. Okay. And at this point, it might not seem like we have introduced any great level of simplicity compared to the metric approach, right? It just seems like a rewriting of the constraints. Okay. So what happens? What is the magic that happens when you look at these Ashtekar variables? Now, the magic, so to speak, arises from, and then you have a third constraint, which is not present in the metric formulation, which is this Gauss constraint. Where is that Gauss constraint? Expression. Okay. So what changes? Okay. So what changes is the fact that so now and again just to mention this, all of this seems like a very complicated route to take. But at the end of the day, when you see the result that you get in this terms of this theory of quantum geometry, you will see that, well, that picture is very simple. And as I mentioned in one of the earlier sessions, that in sometime in the future, when people are taught quantum geometry in the undergraduate classes or maybe in graduate classes, nobody will bother to start with this ADM formalism and go through this whole rigmarole, right? They will just introduce the quantum geometry starting with spins, right? And everybody will just take it for granted that it works. So yeah, I mean, but we are not at that stage yet. We still have to go through we have to jump through all of the hoops, right? Before we can take things on faith. So this transition to Ashtekar variables involves a canonical transformation on this phase space. This canonical transformation involves a rescaling of the densitized triad by a factor of square root of -1 and a translation plus a rescaling of the momentum. So this is the configuration variable, and this is the momentum variable, right? Of course, those two are interchangeable, right? Now, so it involves a rescaling and a translation by this quantity gamma. Okay. Now the thing is, what is this? What is this gamma? This gamma. So you remember that we had a spin connection on the 3+1 spacetime, right? And we had a tetrad. So when we restrict the tetrad to three spatial dimensions, you are left with a triad. What happens to the connection? You will be left with a SU2 connection, omega ij. In this case, it will only have, well, you can write it with two indices or one index, it doesn't matter. SU2 connection on 3-dimensional hypersurface. Okay. And this gamma AI is written as epsilon ijk omega a. So this gamma is related to this omega by multiplication by this one factor. Okay. So again, you can do this because you are in 3 dimensions. So what is this new variable? It is a linear combination of your SU2 spin connection and your extrinsic curvature. And what is this SU2 spin connection? Remember that if you take the gauge covariant derivative and you act on this tetrad, you get 0, right? So similarly, if you take the gauge covariant derivative defined with respect to this three-dimensional connection, then again, when you act on tetrads, you get 0. So how would I define this? I would define it in this way: EABI plus omega A ij E bay j, like this. Or actually, ijk omega aj eb. You can write it either way. You can write it like this, or you can write it like this. It doesn't matter. You can write omega with 2 indices or with 1 index. It's understood that the epsilon is hiding in there somewhere. And this is 0. So that's what this omega is. And this gamma is just the dual of this omega. Dual with respect to this antisymmetric tensor. Okay. Now something sort of magical happens, in a way you can say. This connection, this extrinsic curvature, right? This is not a connection. But this is a genuine connection. Okay. And if you take the covariant derivative with respect to this A that we have just defined, and you act on the triad, what do you get? You get DAEBI plus omega AI omega EJ EBK epsilon IJK, right? This is just the part coming from this spin connection. And then you get a contribution from this extrinsic curvature one form, which looks like this: KAJ EBK epsilon IJK. Okay. Now, this is the nice thing. What happens? You have two parts. One is this part and the other is this part. This part can be written as the covariant derivative with respect to the spin connection of the triad. But this is equal to 0 by definition. And this other one, what is this? This is KAJ EBK epsilon IJK. Well, what is this? This is 0 because this is the constraint. Right? This is the constraint on the extrinsic curvature variable. So as a result, what do we find? We find that this covariant derivative with respect to this connection A, which is called the Ashtekar connection, of this is equal to 0. So in these variables, right, in these Ashtekar variables, so these are your Ashtekar variables, this rescaled connection and your AI, this becomes the form of your Gauss constraint. Okay, this is the statement that your sorry, so this I should be a little bit more careful. I have to you have to write down you have to write in terms of the densitized core triad, and there's a contraction, right? That's why it's called the Gauss constraint. If you don't have this contraction, it's not called a Gauss. So my apologies for that. Okay, so there should also be a contraction here. You can just replace all the B's with A's. And A. Okay. This is your G of I that we defined earlier. G of I was this quantity, right? So now you have this expression is your Gauss constraint, and something nice happens with your Hamiltonian and diffeomorphism constraints. So let me just mention that, and then we will stop for the day. So I will write down now the final form of my constraints. You have the Gauss constraint, which is now this expression, where this is the gauge connection. This is the derivative with respect to your Ashtekar connection. Then you have this diffeomorphism constraint, which looks like this in this FIAB minus AIGI. And then finally, you have your Hamiltonian constraint, which looks like this. FK. So this is Gauss, this is diffeo, and this is Hamiltonian. These are this is called the Ashtekar formula, or the Ashtekar formulation of quantum gravity, of general relativity. So what has happened now? What has happened now is that, first of all, this densitized triad can now be viewed as electric fields which satisfy the Gauss constraint, the same way that in Yang-Mills theory or any gauge theory, you have your electric field, right, which is the which is related. Okay, so which is related to the space-time part of your gauge field, full four-dimensional field strength tensor. Then you have your diffeomorphisms, which again looked a little bit complicated, but now they are looking much simpler. You just have a product of your densitized co-triad and your curvature tensor. And the biggest simplification has come in the form of the Hamiltonian constraint. Now this Hamiltonian constraint, it doesn't have any dependence. There are no factors of 1 by, if you look at the inverse, this Hamiltonian constraint, you see there are factors of 1 by h and all that. Those factors have gone away, and you are left with something that is polynomial in this densitized co-triads. And because it is polynomial, you can find an exact solution. That exact solution turns out to be, you can quantize this system, and we'll talk about the quantization and so on and so forth in the next lecture. Okay, so I'll leave it here. I think this is enough for one day. Okay. And then Friday is Christmas Day. So I don't know, out of you, Takato, are you going to be busy on Christmas evening?
Yeah, right.
Yeah, so
Gonna be busy.
maybe I'll postpone the Christmas Day lecture to next Monday, to the 27th. Okay. All right. So this is the
That would be the 28th though, right? Not the 27th.
oh yeah, 28th, Friday, Saturday, Sunday, Monday, 28th. Okay. Questions?
So I have a question.
Yes.
So in your previous lecture at the beginning, at the very beginning, so we
Yeah.
have talked about Bryce-Dewitt equation.
In the previous lecture, in the last lecture, 1 second, or in
We have
some other lecture.
about Bryce-Dewitt equations.
I talked
somewhere.
about it in one of the lectures, yes. I don't remember which lecture. Let me
Yes.
see. I have to see which lecture exactly. Okay, yeah. So what about that?
The question is, what is the significance of this equation in quantum gravity, or and how do we get for different models? That is. Am I
You're
clear?
talking about you're talking about the Wheeler-DeWitt equation, right?
Yes. Yes, Wheeler-DeWitt equation, right?
Right. So the Wheeler-DeWitt equation is basically you take the Hamiltonian constraint. You take this. You take this Hamiltonian constraint, okay, and you assume, you make the assumption that you can write this kind of an expression makes sense,
Okay.
right? That your states will become functionals of your three metric,
Mm-hmm.
and then you can write down this momentum operator as this functional derivative, right? And then you substitute this in here. Now, in general, for arbitrary spacetimes, this will not give you, this is not something that you can solve, okay?
Okay.
But if you look at something like something symmetric, like a Friedman universe, right? FLRW metric, then your Hamiltonian constraint becomes just the first Friedman equation. And this momentum, it becomes, I think it becomes A dot by A, where A is your scale factor, right? Your three metric is just A, and your momentum becomes A dot. And so there you just treat A and A dot, you just write down the quantum theory of that.
Okay.
Right, basically you take the Friedman equation and you quantize it by saying that A is your configuration variable and A dot is your momentum variable, and you just write the momentum as a derivative with respect to the configuration. Okay. And then you say that, okay, I can solve this equation and I can get states solutions, but those solutions are just functions of A, right? They're just functions of this scale factor, right? Okay. So I mean, it's a sort of a formal kind of procedure. Like it's not clear how to relate that to real geometries or spacetimes. It's not. I mean, at least, yeah. It's not. I mean, maybe one can do that, but it's not clear how to do that. And if you have a more complicated spacetime, like let's say you introduce anisotropies, like the next simplest kind of spacetime, So you introduce, like you talk about some anisotropic this. There are lots of examples, Bianchi spacetime, Bianchi 1, 2, and 3, and so on. Like, then you no longer have just one variable A, right? You get more than one variable. Your momentum operator becomes more complicated.
Complicated.
And,
Yes.
and then your Hamiltonian constraint becomes, I mean, it just becomes horrendous. There is no way to really understand how to solve it. Whereas in the Ashtekar variables, this Hamiltonian constraint for the general case, right? For the completely general case, without any symmetry reduction or simplification, you can solve this constraint exactly in the naive functional approach, in the naive approach in which you treat this as your momentum variable and you write the corresponding operator as something like this. What is your with respect to a connection like that?
Okay.
So then your Hamiltonian constraint becomes an operator which looks like this: f k a b and epsilon I j k, then minus h bar square, then delta a ai delta by delta a bj. Now this object has a very nice interpretation. This object turns out, so okay, yeah, I should not do that. Again, there are some issues about operator ordering and so on. One can always, but neglecting all such issues for the time being, this equation has a very simple solution which is called the Kodama state.
Yes.
And the Kodama state is the exponential, is this functional. There'll be some factor of 1 by h bar or something, I think. And integral over d cubed x of the Chern-Simons Lagrangian associated with the connection. And the Chern-Simons Lagrangian looks like this. Trace of a wedge dA plus 2 by 3 a wedge. So if you perform the functional derivative of this exponential with respect to a 2 times, right, you will get and you add, well, we'll talk about this probably in the next class.
Okay.
But this is an exact solution, right? So this is for the first time that in canonical quantum gravity, one can write down an exact solution for an arbitrary spacetime without any symmetry reduction, right? And then, but it turns out to be more fruitful to perform the quantization in a different way, not in this way. It turns out to be more fruitful to look at the quantization in terms of these Wilson loops, polynomials, and fluxes of the densitized triad. And when you perform the quantization in that way, then you get these states which are the spin network states. Okay. And for a long time, a lot of people in the string theory community had lots of doubts, and they were very skeptical about the quantization, and always they said that, well, you can't do this and this and that. But the irony is that now they are working with tensor networks, and tensor networks are nothing more than spin networks.
Yes.
So if you attend a typical string theory conference, there will be almost no talks on strings but they will all be involving ADS, CFT, and tensor networks. So,
Thank you.
so yeah, I mean, again, see, this is the thing, is that in physics, there is no algorithm, there is no procedural route that one can follow to find what your theory should be, right? I mean, if that was the case, then life would be so much easier. So this loop quantum gravity also has not followed an algorithmic route of discovery, right? I mean, it has been built up based on intuition. There have been choices made along the path that, okay, this is the way you should quantize rather than this. And those choices are ultimately based on some idea or some notion of what form the theory should take, right? But ultimately, the theory, those choices are tested by experiment. And string theory, loop quantum gravity has given a lot of predictions. We are waiting for them to be tested, actually. So it has given predictions about the spectrum of Hawking radiation. It has given predictions about the decay of the transformation of black holes to white holes, tunneling of black holes to white holes, and about the spectrum of inflationary perturbations. And Abhay and two of his colleagues, and one of the authors is actually working at the same institute as me now, Srinath. They have published 2 PRLs, I think, earlier this year, claiming to reconcile the power, the suppression of the power in the low this thing. When you look at the spectrum of the CMB, right? You perform the expansion in this what do you call it? Angular momentum basis, right? L basis. So when you look at the low angular momenta, L is equal to 0, 1, and 2, right? That corresponds to the full sky or half the sky. So there you have large systematic uncertainties in the measurement itself. But if you take those into account, you still get a suppression of the amount of power that should be there in the CMB. And then there are some other issues which are not resolved by the so-called standard cosmological models. So Abhay is saying that, well, you can resolve them. We have to see whether that prediction, well, it's not a predict, whether that model holds or not. But the fact is that loop quantum gravity has given us a lot of information, a lot of material to work with. Another thing that we have got from loop quantum gravity is a way to test for the possible discreteness of time. So people have written papers on that recently. Carlo Dovelli and Marios Christodoulou have written papers on that. And these, and also the testing of the entanglement between objects and how that might be related to or gravity mediated entanglement. That doesn't necessarily come from LQG, but the LQG picture can be used to justify that procedure. And then you have a in the past couple of years, some work by Alejandro Perez and collaborators showing that dark energy can be due to the graininess of geometry, right? And that graininess, that grainy picture, well, that comes from loop quantum gravity, right? String theory doesn't give you that that grainy picture. String theory, people will say that, well, string theory also gives you this space-time form because of this this T duality, I think, which says that if you take a string of a certain radius and you shrink it down, then it cannot go smaller than a certain size. When you go beyond that size, you map to a string which has the inverse of that, from R to 1 by R. So something like that. So, but the problem with this is that you don't really have this. I mean, this string is living in some background space-time. You don't really have a picture of string theory where the space-time itself is non-perturbative. But here we do. We have a picture of a non-perturbative space-time, and we have a picture of quantum geometry and quanta of volumes and quanta of area. So we have this picture of space-time form. And then another very recent paper which won the Gravity Research Foundation Award this year. I think it was by Samir Mathur, if I'm not mistaken. Either Samir Mathur or Maulik Parekh, one of the two. I hope that I'm not offending anybody. But yeah, by Wilczek and Parekh, I think Maulik Parekh and Wilczek, which said testing the noise of gravity using this LISA interferometer. So again, that noise, that gravitational noise, is something that you can calculate in the LQG framework.
Okay.
I don't know if anybody has done that, but I'm sure that it can be done.
Okay.
Yeah.
So in a lighter note, there is a video in YouTube that where Carlo Rivoli and Rapid Busho have exchanged their roles in string theory and LQG. And one defends string, Carlo Rivoli defends string theory and
Really? Okay, interesting.
and that was very funny. So I will share.
Yeah. Sure, you should put that on Zulu.
Okay.
So Rizwan, glad to see that you are still there with your video turned on this time. Last time, I think maybe you had gone to sleep a little bit. Anyway, I'll stop the recording.